Some considerations regarding the visual stimulus. Part 2 by Samuel Renshaw, January 1940. Volume 1, Number 4. The amount of light reaching the retina will vary directly with the area of the pupil. Pupillary size is proportional to the light intensity of the eye opening. The higher the intensity of illumination, the smaller will be the pupillary opening. When we pass from bright sunlight into a dimly lighted room, we see nothing until we become dark adapted. The degree of dark adaptation is customarily measured by the intensity of the threshold stimulus, i.e., the amount of light which can be discriminated from the ground upon which the test patch is viewed. It has been found that after an hour in the dark, the threshold intensity for a normal eye diminished to approximately 1/100,000th of its value in moderate illumination. In the dark adapted eye, the diameter of the pupil will be about 8 millimeters. At 0.01 millilambert field illumination, the size becomes 6.7 millimeters. At 0.6 millilambert, the pupil is 5.3 millimeters. At 6.3 millilamberts, it is 4.1 millimeters. At 126, or maybe 12.6 millilamberts, it is 2.6 millimeters. No, at 126 millilamberts, it is 2.6 millimeters. At 355 millilamberts, it was found to be 2.3 millimeters. And at 2000 millilamberts, the pupil reached its minimum size of 2 millimeters. These measurements are obtained with both eyes open. If a single eye is stimulated, the other being masked or kept closed, the pupil sizes are slightly larger. The light admitted to the retina varies as the square of the pupil diameter. Between the extremes of 2 mm and 8 mm, therefore, about 16 times as much light can reach the retina if the eye is dark adapted than if it is in a strong illumination. But the dark adapted eye is so far more sensitive to light than the daylight eye that the opening of the pupil can account for only a slight fraction of the difference, which must be a change in the chemical and neural responses of the retina to light. This change in sensitivity does not take place uniformly over the retina. Von Kreis studied this problem by having his observers fixate a point source. At the same time, a white surface whose brightness could be varied was presented to the eye at various distances eccentric to the line of sight. When the surface is illuminated by a bluish-white light and the foveal sensitivity was taken as unity, it was found that sensitivity increased quite rapidly, both nasalward and temporalward, from about 1.5 degrees from the fovea and reaches a maximum about 4.5 degrees. Reeves photographed the eye with a motion picture camera to measure the rate of the dilation and constriction of the pupil in the change from light to dark adaptation and vice versa. He found that the opening of the pupil to a maximum diameter in dark adaptation required as many minutes as it requires seconds to constrict to a minimum in bright light. From the faintest to the maximally tolerable brightness, the range of light intensities is very great. The threshold for brightness in the dark adapted central field is about 0.275 microwatt per square meter of illuminated surface. A microwatt is a millionth of a watt. 1 watt represents the expenditure of 10 million ergs on energy per second. An erg is approximately the energy required to raise a gram weight 0.01 centimeters against gravity. On the periphery of the retina, the threshold is only about 1/1000th of the value for the macula. The above figures represent a large stimuli. Very small point sources, like stars, show even more strikingly the sensitivity of the retina. To quote Boring, the power of a faint star, visible in peripheral vision, is about 10 to the 8th microwatt, or 10 million millionths of a watt, 1,000 millionths of an erg per second. Such a star would have to shine on the retina for 40 years to deliver an erg of energy to it. If it can be perceived in a fifth of a second, as seems probable, then the retina is some 30,000 times as sensitive as the most sensitive radiometer, which the physicists use for measuring radiant energy. Thus we see the intensive range of light which the eye can discriminate from the faintest to the brightest intensity represent an enormous range. However, if you take a white of the order of brightness of a sheet of white bond paper reflecting the north sky at noon and a black of the approximate coefficient of reflectance equal to printer's ink, we may ask how many just perceptible steps of brightness can be discoverable in this achromatic series which will vary from white through neutral gray to black. This experiment has been made a number of times by different investigators. The method used has conventionally been the method of minimal change. If we start with a standard white and then make a comparison surface just perceptibly darker than the standard, measure the difference, and then take this new value as a standard and repeat the procedure. We can thus determine the number of steps, sometimes called J&D units, or just noticeably different steps within the brightness range of black to white. It is obvious that the number of such steps will depend upon the intensity of illumination, upon the state of adaptation of the eye, and certain other factors which need not be mentioned here. In contrast to the enormous range of physical brightness, the number of J&D steps from white to black under 20 apparent foot candles varies with different observers from about 160 to 350, with the average at approximately 210. Thus the eye can make approximately 200 discriminations of brightness of a surface, namely, white paper reflecting the north sky having a coefficient of reflectance of about 0.82 to black having a coefficient of about 0.05. Within these limits there are about 200 discriminable shades of blacks and grays and whites. Perhaps the earliest experiment of this kind was made by Bourguier in Paris in 1760. In 1858, Fechner noticed that the ratio delta I over I was approximately constant regardless of whether I, that is intensity, was large or small. This value has been found by various investigators to be approximately 1%. In other words, 1% of any intensity of illumination except the very highest or very lowest added to that illumination will make it just perceptibly brighter. This is really Weber's law and was announced in 1834. It says merely that the ratio delta I over I is a constant. Fechner expanded the concept by assuming that all discriminable increments of sensation were equal, and by assuming these increments to be infinitesimal and integrating, he obtained the equation S equals K log times I over I original. This is a formula for Fechner's law, which became the basis for a tremendous amount of subsequent work on the problem of the measurement of intensity. Using crude telescopes not much better than the average opera glass, the early astronomers classified the fixed stars into groups of 6 magnitudes, the brightest being the first and the faintest visible stars. The brightest being the first and the faintest visible stars, the 6th magnitude. To the eye, each magnitude is just noticeably brighter than the magnitude preceding. Thus, the 6 magnitudes represent equal sense distances. These relations can be expressed as m equals c minus k log times I, where m is the magnitude of the star, I is the quantity of light reaching the eye from it, and k is the constant which has the approximate value of 2.5. When the magnitude increased one step, log I increased by 0.4, and the light reaching the eye from the star increased 2.5 times. This follows from Fechner's law. The light had to increase 2.5 times instead of 1.01 times in the case of stars because stars are point sources instead of extended surfaces. Since these early times, and using greatly improved instruments of precision, the value delta I over I has been determined by several investigators with great accuracy, and although separated by a half-century, with almost perfect agreement, so that in the present day, light intensity relations can be specified with considerable assurance for persons possessing normal vision. The pattern of precision work was really set by the investigation of Koenig and Brodun. Observations were made on some small differences of intensity in terms of an arbitrary unit which ranged from 0.002 to 1 millionth of these units. Observations were made not only for white light but also for wavelengths 670, 605, 575, 505, 470, and 430 mu. Koenig's intensity unit has subsequently been found to equal 0. millilambert. More recently, these observations were repeated by Blanchard, Ives, Priest, Houston, Hecht, and others. An interesting development arose from a comparison of the curves obtained for white light and the various colored lights. Out of this work, there was developed the observation first made by the great Austrian physiologist Purkinje, which is called the Purkinje effect, namely that in daylight adaptation, the brightest part of the visible spectrum lies in the vicinity of wavelengths of 556 mu, and in scotopic or twilight vision, the point of maximal brightness shifts from this position in the yellow to 511 mu, which is in the region we call green. It was noticed that if a red light and a blue light were being equated for brightness, using a simple instrument like a Bunsen grease spot photometer, and the observer equated them with his eye close up, that is, from 2 feet distance, and then repeated the observation from about 20 feet, the obtained values were not the same. This was due to the fact that at a greater distance the eye becomes more dark adapted, and with it came a greater change in the relative brightness of the blue and red lights. The following figure illustrates the visibility curves of human vision for both the scotopic and photopic adaptations. The photopic curve represents the light-adapted eye. The scotopic one represents the dark-adapted eye. These two curves should be studied very carefully because they are of great importance. The visibility scale representing the ordinates is determined by setting the spectral light of highest brightness at unity. For the daylight eye, wavelength 554 to 556 mu represents this point. The spectral hues of visible light are all contained within the range from about 400 to 700 mu. The red band extends from about 647 to 760, orange 588 to 647, yellow 550 to 588, green 492 to 550, blue 433 to 492, and violet 390 to 433. Within this range, Jones found that 128 just perceptibly different hues could be discriminated. Thus it will be noted that the number of hues in the visible spectrum is considerably smaller than the number of achromatic steps within the range of light intensities. Thus, referring to Figure 1, in photopic vision, a bluish light of wavelength 540 would have only about half the visibility of a red light of a wavelength 650. From the curve, it can be ascertained immediately that when the eye becomes dark adapted, yellow at wavelength 550 is reduced from a visibility of 1.0 to approximately 0.5. From studies on the intensity relationship of lights of various wavelengths, the duplicity theory of von Kries was produced. According to this theory, vision at the high intensities is carried on by the functioning of the cones, and at low intensities, when the spectrum appears colorless, by the rods. Rods and cones were held to have separate and independent visual mechanisms. The rods, having a lower threshold than the cones, came into action earlier when intensity is raised from 0. Within a certain range, both mechanisms contribute their parts to the sensation, but at high intensities, the cones dominate the scene and render it more or less immaterial as to whether the rods are active or not. There is considerable evidence both for and against the duplicity theory, which has gained for itself almost universal acceptance for the simple reason that no other more satisfactory theory has been proposed. Recently, Parsons and Lithoge and Tansley have shown that under certain circumstances, rods may act like cones, and that certainly cones seem to be dependent upon chemical exciters produced in the rods, for without the assistance of this substance, the cones fail to perform their customary functions. The eye is a photometric instrument of great precision. When proper understanding of its structure, function, properties are attained, greater care of such a valuable instrument will be taken.